The United States has some of the greatest bridges ever built. The Golden Gate, the Brooklyn Bridge, masterpieces of engineering that define what humans can accomplish. But there's something happening in China right now that makes every single one of them look small. And it's not bigger because it's better, it's bigger because Western engineers said it was impossible, then China built it anyway, and now they're building something even more insane. Imagine a road that doesn't end where the land ends. It keeps going, past the beaches, past the last visible shoreline, out over open ocean, where the water is deep enough to swallow a 10-story building in one gulp. And then, just when you think the road has to stop, it doesn't. It disappears, completely. It dives underwater through a tunnel resting on the seabed. A tunnel so deep that the largest cargo ships in the world pass directly overhead without ever knowing a highway is running beneath them. This isn't a bridge, it barely even qualifies as a road. But here's what makes this story worth your attention. This tunnel was built to survive something that would destroy almost every structure on Earth. An 8.0 magnitude earthquake, a Category 5 super typhoon, and a direct collision from a fully loaded cargo ship traveling at full speed. All at the same time, if it had to. American engineers looked at the blueprints and said one thing: it cannot be done. China built it anyway. Before you can understand why this crossing seemed impossible, you need to understand what it was trying to connect. The Pearl River Delta. 3 cities, Hong Kong, Macau, and the mainland city of Zhuhai. On paper, they're neighbors. In reality, they were separated by 55 kilometers of open water. Not a calm bay, not a protected strait, a stretch of the South China Sea that sits directly in the path of some of the most violent typhoons on Earth. For decades, moving goods between these cities meant a choice. Drive nearly 4 hours around the entire delta on congested mainland roads. Or load your cargo onto a ferry and hope the weather held. There was no direct route, not because nobody wanted one, but because nobody believed one was possible. Think about the scale, the Golden Gate Bridge. The bridge most people picture when they imagine great engineering stretches less than 3 kilometers. This crossing needed to be almost 20 times that length. Over open sea, not over calm water with controlled conditions. Over water that actively fights back. And here's where it gets complicated. Running straight through the middle of this crossing zone is one of the busiest shipping lanes on the planet. Hundreds of massive cargo vessels pass through every single day, some carrying over 20,000 containers. That meant any bridge built across this water would have to be tall enough to let those ships pass underneath without slowing down. But the shipping lane also sat directly beneath the approach path for Hong Kong International Airport, one of Asia's busiest airports. A bridge tall enough for ships would be too tall for planes on final approach, and you can't ask a plane landing at full speed to suddenly climb higher. This is where most countries would simply give up. They'd accept the 4-hour drive. They'd accept the ferries. They'd accept that some distances are just too far to bridge. China's engineers looked at the same impossible problem and designed something nobody in the Western world believed could work. Before engineers could even think about building, they had to understand what they were up against. And the Pearl River Delta doesn't play fair. Start with the weather. This region sits directly in the path of some of the most violent typhoons on Earth. We're not talking about storms. We're talking about rotating systems of chaos, with wind speeds exceeding 250 kilometers per hour. That's fast enough to flip a truck, fast enough to turn ordinary objects into projectiles. In 2018, Typhoon Mangkhut hit this exact region, with sustained winds of 162 kilometers per hour. Trees snapped like toothpicks. Buildings lost their roofs. Ships in the harbor broke free from their moorings. Any structure built here would have to survive that. Not once, but repeatedly, over a 120-year lifespan. But weather was only the beginning. Beneath the water sits the seabed, and this isn't solid rock, it's soft marine clay. The kind of material that moves, that shifts, that can swallow a badly designed foundation over time like quicksand. Engineers call it liquefaction risk. What that actually means, your foundation could sink, your structure could collapse, Not because you built it wrong, but because the ground beneath it decided to stop holding it up. And then there's the traffic. Hundreds of cargo vessels pass through this water every single day. These aren't small boats. Some weigh over 300,000 tons. They carry over 20,000 shipping containers stacked on their decks. If one of these ships veered off course, or experienced engine failure, and collided with your bridge, the impact would be catastrophic. Most bridges in the Western world aren't even designed to withstand a direct hit from a fully loaded cargo ship. The probability is considered so low that engineers typically ignore it. China's engineers decided to plan for it anyway. So now imagine this. You're designing a structure that has to be tall enough for massive ships to pass underneath, strong enough to survive typhoons that could level cities, built on seabed that's essentially unstable, while handling the constant stress of being hit, potentially, by a 300,000-ton moving object. And you have to do it in a way that doesn't block planes from landing. This is the moment when Western engineers stopped laughing and started paying attention. This is the moment when China's engineers did something almost nobody in the world had attempted at this scale. They refused to choose. Most engineering problems force you into a single solution. Build a bridge or build a tunnel. Pick one. Live with the consequences. But this problem had competing demands that made a single solution impossible. You needed height for ships. You needed concealment for planes. You needed strength for typhoons. You needed speed because the timeline didn't allow for decades of construction. So instead of choosing, they designed something hybrid. For most of its 55-kilometer length, it's a bridge, a conventional bridge, 6 lanes wide, elevated high above the water, strong enough to handle the constant weight of traffic, while typhoon winds rage beneath it. But as the structure approaches the busiest section of the shipping lane, something unprecedented happens. The bridge doesn't continue. It sinks. The roadway descends onto 2 artificial islands built specifically for this purpose. And between those 2 islands, it disappears completely. It becomes a 6.7-kilometer undersea tunnel, over 4 meters of roadway sitting on the ocean floor, deep enough that the largest container ships in the world can pass directly overhead with room to spare. Planes on approach to Hong Kong Airport never know it's there. Think about what that actually requires. You're not digging a tunnel through solid rock the way engineers usually do. You're assembling it piece by piece on the seabed itself, in a stretch of ocean known for violent storms and shifting currents, with a margin of error smaller than the width of a human hand. One section misaligned, one seal that fails, one miscalculation at depth. Game over. And here's what made Western engineers genuinely concerned. This technique had never been attempted at this length, this depth, or in waters this exposed to typhoons. They weren't just building something big, they were inventing a new way to build something that shouldn't exist. Building an underwater tunnel isn't like building a regular tunnel. You can't dig. You can't shore up walls as you go. You have to assemble it like a puzzle, underwater, in the dark, where one mistake ends everything. The engineers designed 33 massive concrete segments. Think of them like enormous rectangular blocks, each one roughly 180 meters long, each one weighing around 80,000 tons, heavier than the Eiffel Tower, repeated 33 times over. Here's how it worked. These segments were built on land, one by one, perfect conditions, climate control, inspection at every stage. Then each completed segment was floated out to the construction site on special barges, positioned with millimeter precision over its exact location on the seabed, and then sunk, all the way down. But sinking a segment isn't like dropping it. You can't just release it and hope it lands right. The engineers had to control the descent, manage water pressure, account for currents that could push it off course, and guide it down to connect perfectly with the segment already below it. Divers worked at depths where visibility could drop to almost nothing, where currents shift without warning. These weren't casual dives, they were precision operations, guiding segments weighing tens of thousands of tons into alignment, with tolerances smaller than a few centimeters. If a segment landed wrong, it wouldn't just delay the project, it would potentially ruin years of work. The entire structure could be compromised. But here's what happened that shocked international engineering observers. All 33 segments installed, zero significant rework required after placement. An outcome many experienced tunnel engineers considered close to impossible at this scale. The precision wasn't even close. It was millimeter perfect, repeatedly, 33 times in a row. And that was just getting the segments in place. The real nightmare came next, sealing them, creating watertight seals between 33 neighboring segments so that not one drop of seawater could ever find its way inside. At depth, under pressure, with ocean currents testing every connection, if even one seal failed, water would pour in. A 6-lane highway would flood. A catastrophe would unfold in slow motion beneath the ocean. Before the tunnel could exist, the islands that anchor it had to exist first, and neither of them was there. Engineers needed solid ground in the middle of open ocean, in water up to 44 meters deep in some sections, on a seabed made of soft marine mud that couldn't support a foundation using traditional methods. You can't just drop concrete pillars into mud. They sink, they shift, they collapse over time. Traditional land reclamation would have worked. Dump rock and sand into the water until an island rises. But it takes years. And this project had a timeline measured in months, not decades. So the engineering team designed something that had never been used at this scale anywhere in the world. Enormous hollow steel cylinders, some as tall as a 20-story building, driven directly into the seabed like giant drinking straws pushed into wet sand. Except these weren't small. They were massive. Each cylinder wide enough to drive a truck through. 120 of these steel cylinders were sunk into position, forming a solid ring. Once locked into place, the space inside was filled with sand and rock, creating a stable artificial landmass. 2 artificial islands, built in roughly 1 year, a process that conventional reclamation methods would have taken several times longer to achieve. But here's what made this genuinely innovative. The cylinders had to withstand typhoon winds. They had to resist the constant pressure of water pushing against them. They had to stay locked in place while being filled with millions of tons of material. The large diameter steel cylinder method. Never attempted at this depth. Never attempted at this scale. Never attempted in waters this exposed to storms. These islands weren't just land. They were engineering statements. Proof that the team could solve problems nobody had solved before, and they were only the foundation for what came next. Every part of this crossing was designed around a single number, 120 years. That's how long the structure is engineered to last. More than double the design life of most major bridges built anywhere else on Earth. In the United States, the average major bridge is designed for a lifespan closer to 50 to 75 years. This had to survive twice as long. To hit that number in this specific location, engineers had to design for the absolute worst-case version of nature. Not the probable, not the likely, the absolute worst. The bridge and tunnel system is rated to withstand an earthquake measuring 8.0 on the moment magnitude scale, strong enough to be counted among the most powerful earthquakes ever recorded on the planet. We're talking about the kind of seismic event that would level cities, that would crumble most structures into rubble. It's rated to withstand a super typhoon, with sustained winds, strong enough to be classified at the very top of the tropical cyclone scale. The kind of storm intensity that would shut down entire cities and ground every flight in the region. The kind of wind that doesn't just break things, it erases them. But here's the detail that stunned engineers when it was first published. The bridge's support pillars were designed to survive a direct collision from a 300,000-ton cargo vessel traveling at full speed, roughly the weight of the largest oil tankers on Earth, without the structure collapsing. For comparison, most Western bridges are engineered around a maximum designed vessel far smaller than that, because a collision from a fully loaded supertanker is considered such an extreme unlikely event that most bridge designs anywhere else in the world don't plan for it at all. In the Pearl River Delta, with hundreds of massive ships passing daily, engineers treated it as a scenario they had to design for. Not around, for. Not as a possibility, as a requirement. The engineering numbers tend to dominate the conversation. The tonnage, the distances, The specifications. But underwater construction on this scale comes down ultimately to human beings doing extraordinarily dangerous work far from any camera. Roughly 9 years passed between the start of major construction and the crossing's opening. Tens of thousands of engineers, welders, divers, and laborers involved across the full length of the project. At its peak, thousands of workers were on site every single day. But underwater, it was different. Specialized diving teams performed thousands of individual dives to inspect, align, and seal the immersed tunnel segments by hand, at depths where visibility could drop to almost nothing, where currents could shift without warning, where the pressure was enough to crush a human body if something went wrong. These weren't casual dives, these were precision operations. Divers worked with instruments to guide segments weighing tens of thousands of tons into alignment, fully aware that a miscalculation wasn't a minor error. It was a project-ending failure. It was potentially catastrophic. Engineers on the surface described the sealing of each tunnel joint as one of the most tense phases of the entire 9-year build. Every one of the 33 seals had to hold under enormous water pressure indefinitely for the structure to be considered safe for public use. There was no way to fully test a seal except to complete it and monitor it under real conditions, which meant the first time they'd know if a seal would hold was when the tunnel was already filled with water, when it was already too late to fix it. This is the part of mega-project engineering that rarely gets highlighted in headlines about world's longest or world's biggest. Somewhere beneath the surface of the South China Sea, ordinary construction workers and engineers spent years solving a problem that had never been solved at this depth or this scale anywhere on the planet. Very few of them will ever be publicly recognized for it. It's worth pausing here because this is where the comparison usually gets misunderstood. The United States has incredible bridges. The Golden Gate remains one of the most recognizable structures on Earth. Japan's Akashi Kaikyo Bridge held the record for the longest suspension bridge span in the world for decades. Denmark's Great Belt Fixed Link combined a suspension bridge and undersea tunnel across roughly 18 kilometers of water. These are genuine engineering achievements. But scale changes everything. The Chesapeake Bay Bridge Tunnel in Virginia, completed in 1964, was actually the first crossing in the world to combine a bridge and tunnel system. For decades, it was considered one of the most ambitious engineering feats in American history. It runs a little over 28 kilometers. This Chinese crossing runs 55 kilometers, almost double the length, through far more hostile ocean conditions, using tunnel immersion techniques refined decades after the Chesapeake was built. Aimed at surviving typhoon and earthquake conditions, the Chesapeake was never designed for. The honest comparison isn't that China did it better than the engineers who came before. It's that China took a technique the world already understood in a limited form and pushed it further than anyone had ever attempted. At a length, depth, and hazard level, nobody had previously combined into a single structure. That's the part that consistently catches Western engineers off guard. It isn't that the idea was new. It's that nobody else had been willing or able to build it at this scale, in this amount of time, in water this dangerous. China didn't invent the bridge-tunnel hybrid. China just proved that the impossible was only impossible because nobody had tried hard enough. But here's what most people don't know. This crossing wasn't just infrastructure. It was a prototype, a proof of concept, a demonstration that China had solved a class of engineering problems that had stopped other countries from attempting similar crossings anywhere else on the planet. And China is already building the next one, the Bohai Strait Tunnel, 123 kilometers long, deeper water, stronger currents, more extreme conditions. A tunnel so massive, it would make this one look like a warm-up exercise. Western engineers are already looking at the blueprints, and they're already saying the same thing. It cannot be done. Which means we know exactly what's going to happen next. China will build it anyway.